Going over some of the few things that have to do with molecular structure. Okay, like I said, this unit is mostly going to be talking about molecules which share electrons, although we will touch on a little bit of the structure here for the ionic compounds as well. Structure is important when it comes to developing new drugs or new products, and a lot of the shapes and the way that even the larger organic molecules, the way that the shapes and how that you put together the smaller shapes does make a difference as to how they're going to be able to work. So structure does matter. So a lot of pharmaceuticals, a lot of things to make the drugs more effective in their uses, and scientists have to design these things in order to make sure that they're effective. Now, for ionic compounds form what we call a lattice structure. Lattice structure is a repeating pattern that alternates the cations and the anions. Now, this particular one up here is showing you sodium chloride, where it's like a negative and then a positive and then a negative and so forth, and it's repeating. Not all ionic compounds have a 1-to-1 ratio, so their patterns may not be 1-to-1 like this, but they do have a unit cell pattern that they follow. And you can see here, kind of looks like a very much so like a cuboidal type crystalline pattern. And the ionic compounds and the metals will follow this kind of lattice structure when they're building. So like a crystal or a chunk of metal will follow a lattice structure similar to this as well. Why I did that, I have no idea. Let's go back here. Come on. There we go. So we can move on back to the nope. All right, sorry about that. Moving on. All right, so molecules are covalent compounds. They share electrons. All right, so the pattern that you were seeing when you were doing the PhET simulation is based off of this idea of valence shell electron pair repulsion. And it concentrates on an idea that electrons arrange themselves in a 3D structure to be as far apart from each other as possible around a central atom. So the shared electron pairs repel one another. So these ones in the bonds, they're going to repel each other, as well as the lone pairs, which in the model, they use the little cloud thing with the 2 dots. The lone pairs take up a little bit more space, okay? But all of them, lone pairs or bonded pairs, are going to repel one another, so they space themselves around the central atom to be as far apart from one another as possible. The whole point of the VSEPR theory. Okay, VSEPR allows us to predict the shape. Okay, and a lot of the molecules have like a 3D dimension to them. So if it does, like the pyramidal and the tetrahedral ones, we use lines for it to be in the plane with us. We use wedges. You can draw them like this, wedges, to show them coming out from the paper, and then you do like dashes. I'm not very good at the dashes, by the way, but you make them longer as you go and shorter coming in to make them look like they're going backwards, okay? So you'll see me drawing these when we're looking at the ball and stick model or the 3D structures, okay? And you need to also make an effort to draw them appropriately. So if you have A to B, which is just point A to point B, it's always going to be linear because that's a straight line. But you can also have a central atom with 2 outside atoms, okay? And an example of that is carbon dioxide. So here, so you can see the first ball and stick model here shows you, hold on, I'm trying to change the color. The first ball and stick model here is showing you the A to B, so this would be like H and this would be like Cl here. Okay, but if we're looking at like carbon dioxide, or O and the C and the O like that, as you probably saw in your simulation that you just did, okay? And you see that they are in a linear pattern straight line, okay? The second type here is the bent shape, okay? And that's also got one central atom with two atoms attached. So two bonded and two lone pairs. Does it have lone pairs? Yes, it does, okay? Now here you can draw it this way and you can include the lone pairs like it does in the simulation, like so. Or you can just draw it like this, where you have one like this. And let's see here, let's change color. Come on. So we have like this, where you do not include the lone pairs. You can draw it like that too. That also would qualify. Now, when you add on a third bonded atom, AB3, now you have three bonded. That's where that tri comes in here. We know tri means three, so at least three atoms would be attached, okay? It becomes a flat triangle, like so. Flat triangle, and if you know flat triangles, they basically are gonna have 360 degrees there, so each one would be about 120 in that particular deal. But basically you have three bonded atoms and no lone pairs. So a couple of examples here, SO3, BH3. Remember, boron is one of those exceptional ones where you only do 6 valence electrons and 3 bonds. Okay, moving on to the pyramidal one. So for pyramidal is also AB3, so that means 3 things are attached as well, 3 bonded atoms. However, when we're talking about trigonal pyramidal, you do have a lone pair. You have at least one lone pair. So here it's going to look like a mini pyramid, and this is where you can still keep the lone pair there at the top, but you do need to draw this one more three-dimensional. So here we have our atom, okay, and we're going to draw showing 3 dimensions here. Going to switch over to new color. So we have one in the plane. We need to do one that's a wedge, like so, and then we need to do dashes to show the other one going backwards, because this is a 3-dimensional structure. And then you could put your other, atoms down here. So one showing it's coming forward, one showing it's going back, and one showing that it's in the plane. So that's what we mean by wedges and dashes when you're drawing these, to make sure that you're including them. The pyramidal one has 3 dimensions, as you saw in the PhET simulation, but here I also have a hand model that you can pass around and look at. The purple one at the top is the lone pair, but as you can see, it's like a mini pyramid. Okay, so go ahead and pass that around. The last one here that we have to contend with is our tetrahedral shape. Okay, so for tetrahedral, oh, come on. This board is so not workable. Okay. Here, tetrahedral is going to have tetra, prefix 4. That means there's 4 bonded atoms attached. There are not going to be any lone pairs, so no lone pairs. And what you'll notice is this one looks like the mini pyramid one, but it also, instead of having a lone pair at the top, it has a bonded atom. So this one also has to be drawn 3-dimensional. Okay, so here I'm going to try my best. I'm going to put the one in the center here, and let me get my black going on here. So we have the one going up. We have one in the plane. We need to do the wedge, color it in a little bit, and then the dashes. like so. And I'm going to make the other atoms a different color for fun. So this will be blue, this will be blue. So on the pyramidal and on the tetrahedral, make an effort when you're drawing the ball and stick model or the 3D structure to show that they are three-dimensional. I also, some examples here, you know, CH4, you'll notice there's 4s in the molecular formula there. Also, when you're looking at the planar versus the pyramidal, they all have 3s, but the difference is the planar doesn't have a lone pair, whereas the pyramidal does have a lone pair, okay? And that's also kind of the difference between the bent and the linear. The linear will not have lone pairs, but the bent will have lone pairs. So pay attention to that, and when I say will have lone pairs, I'm talking about on the central atom, okay? We're talking about how many atoms are bonded and how many lone pairs are on the central atom will determine the shape, okay? So here, make sure that you're taking a look at this. You can always use the PhET simulation to your advantage when you're doing some of the work here. But you want to draw the Lewis dot structure. You'll want to determine how many bonded, how many lone pairs on the central atom, and then you can go from there to determine the shape.